in the actual room. So very excited about kind of the rest of the semester when we can see each other. So I'll be doing a lecture today on the system interconnects. And I think we'll see how fast we go through stuff. It may spill over into Thursday. And Sophia will pick up with a lecture on tile link and some kind of very specific types of system interconnects. But this lecture is more geared to kind of introduce you to the very broad topic that kind of is a course in itself. So hopefully you'll just pick the most interesting pieces and be able to pursue that further if you're interested. I mean, you've already seen this plot before many times, but I kind of wanted to add a different angle to this. So if you look historically, people have been, of course, pursuing clock frequency boosts. That's like prior to 2000s. And then since that had to stop because of the power limitations, they had to figure out how to continue improving performance, mostly through parallelism, right? Now, for general purpose machines, parallelism is limited. You have several different mechanisms where you can kind of exploit parallelisms in the program. And then mostly you have to go back to like data level parallel, which people tried to do in those days. And then in the end of the day, just had to start replicating cores that would do individual threads of different like virtualization and things like that as the data centers started rising. And that's where you see kind of from 2005 and onward, the number of cores, even for general purpose machines per CPU, started increasing very rapidly. Another kind of hidden part of this thing is that the yield started being limited in these more advanced processes. So it was easier to kind of print the same thing many times and then use some sort of a network and then enable, you know, a different number of cores depending on the product bins to kind of recover the lost yield of some cores not working on the die. It also makes the packaging cheaper because if you activate a smaller number of cores, you don't have to have as expensive a package and power delivery network and all of that. So all of these factors kind of contributed to that. But the thing that people had to start inventing in this period of time was exactly this type of system interconnect. How do you connect all these cores together on the chip? How do you connect them to the external memory and things like that? So these are kind of interesting historic data to look at. Of course, we're like in 22 now. But you know, back in the day around 2009, 10, these big general purpose processors have just started including 4, 8, 16 cores, so at the very beginning. But there were like startups like Tylera, for example, who were trying to push smaller cores, many more cores, right? And those were really the ones that started pushing the kind of extreme demands on this on-chip interconnect. How do you actually wire all that up? And the reason why I'm showing this, it's kind of always nice to go back to look at history, because when you compare to where things are now, you'll see kind of where the roots of these innovations started happening and how today's systems are leveraging all that. Before this time, these types of interconnects between cores and memory or big unified shared memory only existed in high performance computing. Big Cray machines have had essentially a unified shared memory among all the processors, but that was like a rack level. And so no one really knew how to design these things so that they're small and compact, fit on one chip and don't have all these protocol overheads, because now every kind of joule of energy or picojoule of energy actually matters quite a bit, and the speed matters, right? And so people started advocating for kind of doing these very regular, replicated, easy to design chips, because you design one small core, replicate it across the chip, you design a very repeatable kind of on-chip network, and then with a little design effort, you have a big chip doing something, right? That was kind of the mentality, right? This is just to give you some numbers of what people are shooting for. If you're designing a small core, you can obviously boost the clock frequency because you're not as deep doing parallelism or out of order and things like that. And then get pretty high overall throughput. Now, how much of this throughput is actually being utilized in applications when all the cores are running, that's a different story, right? Because you have to have a workload that can map to all these cores to run them. And then, to use all this on the chip, you have to have about 5 to 10, byte per flop is usually kind of a good rule of thumb for the off-chip bandwidth. Of course, no one is at 1 byte per flop, right? That's like a holy grail. People are usually at 0.1, 0.05, 0.01 byte per flop in a lot of these applications. So when they report these numbers, it's really just link pack running in place on cores, right? So, it's kind of like, these are the early many core machines like Sun Niagara. This is mostly database kind of workloads, Intel network processor, IBM Cell. If you had a PlayStation 3, that was kind of the processor there with many DSP cores and some general purpose. And really kind of the point of this is that as you amass more cores, there was at some point an idea you're going to have 1,000 cores on a processor, and Intel's Knights Landing kind of started getting very close to that, but then of course failed because it was very hard to map the applications to such architectures, right? You have to find the right application to be able to leverage this massive parallelism. And if you're just instantiating general purpose cores on the chip, it's very hard to find an application to do that, except if you're doing massive virtualization. So really every core is to themselves. Right? But it's kind of nice to think about, when things got started in 71, that was actually before I was born, you had like 2,000 transistors on a chip, and you made a processor. Now, depending on what core you're designing, you actually have thousands of cores per piece of silicon or per package, right? So it's kind of like a mind-boggling exercise to think about. The processor is like the new transistor, right? So you have to think about these higher level building blocks now, and how do you put them to good use on silicon. So once you start adding more compute units, you have to start thinking about how do they interact with each other, right? So what's the interconnect network that connects the CPUs, let's say, and cache on the chip? Is the cache private to every CPU? How do you manage coherency across that? NUMA is non-uniform memory access is actually really painful to program. You would rather have uniform memory access and big shared memory, but that adds a lot of overhead on the interconnect network, right? And so people started thinking about all these things, how to put it together, and that adds a lot of constraints on this one. Of course, in 151 to 51A, we start talking about wires and problems with basically wire congestion, capacitance, energy. So all of these would contribute to on-channel bandwidth limitations and latency, as we'll see later. And then you have this other interconnect network between your cache and DRAMs that sit outside. They could, in modern technologies, as we'll see, sit on the package like HBM, high bandwidth memory, or somewhere kind of on the board. And you have to kind of balance out these two interconnect networks, because if you over provision this internal one, it will only serve the applications that can fit in the cache at the expense of kind of the other interconnect network. Unfortunately, the power limitation for the package applies to everything, right? So you have 200 watts, 300 watts, you have to allocate it very carefully to every resource in the package to try to balance the system. And that's kind of where Amdahl's law also comes into play. You have to see which part of the system is most sensitive, who the application is the most sensitive to, right? And then you go and improve that part of the system, but only so much until other things pop up. And you start basically playing whack-a-mole, where you're trying to push down things to which the application is the most sensitive to, right? So it's kind of a delicate balance of all these things. So how do we go and scale to many cores? So one way to do it is basically to say, okay, well, I'll have a CPU over there, and I'll just add a little switch router next to every CPU, make the architecture very regular, right? So it's easy to kind of just print on the chip, and they'll basically just connect all these up together, create something that's called a mesh network on chip. These are easy to build, easy to kind of make sure they work, but they're slow, and latency there, as we'll see, varies greatly on the traffic pattern. Who do I want to reach? Do I want to reach the nearest neighbors, or do I want to go all the way to kind of the other end of the die, right? The number of hops through the routers starts increasing, and so will the congestion, depending what traffic patterns you have kind of among all of those. Then the other extreme are basically large crossbars. Wouldn't it be nice if I had just a ginormous switch somewhere in the middle, and every processor just attaches to it, and in one clock cycle or a few clock cycles, the traverse switch basically just gets across, right? That would be really great. But these large crossbars are basically very hard to build and scale, right? As the number of ports or the number of processor grows, that's harder thing to do. And there are other types of topologies that we're going to go through. One example is a ring. A ring is actually very popular for smaller number of cores, 8, 16, etc. You can find it a lot in cell processor, in some of the a lot of the Intel architectures. Actually, it's kind of a simple, also scalable, but it has its own routing limitations and power and latency limitations. So there's a whole like range of networks that people are playing with to try to balance this power, bandwidth, overall system throughput kind of space. This is another example of the early crossbar, where this was like a radix 16. So Rainbow Falls had 16 cores. And if you look at kind of this space of what we call memory semantic fabrics, right? These are not TCP/IP Ethernet style networks. You're really trying to route around either register 64-bit type of units, or like a cache line size units, 512, 1024 bits. And you don't want to have like a huge protocol stack. So the most you want to have is basically flow control, as we'll see later, to just know where you're going and is there a congestion, right? So you want to execute things very quickly. And there's really no software running here. It's all hardened essentially in the hardware itself, right? Because it needs to be very power efficient and very fast. And so it's very important to kind of look at all these overheads and try to shave them off as you're doing stuff. So in these types of networks, like a radix 16 router is really kind of 16, you'll see later some examples, 18, 20, but not like 6428. Those crossbars are very big routers, and people build them really for more like networking fabrics in the backbone of the data center, right? Because they can afford to have big chips with lots of latency and things like that. So what are today's trends? Well, on one hand, we have people who took this concept of on-chip network to the very extreme. So I like this fun photo of Cerebrus. This is Vaporscale Engine 2. So it's not like a gimmick. This is really a whole wafer. They just cut out the round edges. It's a 12-inch pizza style size chip, which of course consists of a replicated design many times. So across the reticle itself, and then of course reticles get printed across the whole wafer. They do reticle to reticle stitching so that you can extend the network from one reticle to another reticle, right? And that way create this like massive processor. If you look at it, it's at 2.6 trillion transistors and 850,000, let's call them AI cores, right? These are not really your general purpose cores. These are basically matrix vector optimized cores, but smaller ones, I would say. They're not the size of the typical general purpose core, not even, I would say, the rocket core. But it burns 15 kilowatts of power. So think a little bit about that. You know, your stove burns, so it's basically 15 kilowatts is about 75 really power-hungry server processors, right? It's in one little piece. So how do you deliver at 1 volt of supply? This is 15,000 amps. That's like a copper pipe, this thick, just to attach to this to provide current, right? These are some really crazy numbers, but people have built it. And because of that, they can add a lot of SRAM to the chip itself. 40 gigabytes. Just to give you an idea, we'll show you later, on even here, next generation Intel GPU is 120 gigabytes on these 8 HBM stacks, right? So it's kind of comparable, but this is DRAM, this is SRAM, this is super fast. This is like a clock cycle to access, right? Well, it's clock cycle to access to a local AI core. Still takes quite a while, given the type of network they have, to be able to go from this core to this core's SRAM, right? Because SRAM is not centralized in one place, it's basically distributed all over the place, right? The design is kind of replicated. So they have kind of enormous 20 petabytes per second SRAM bandwidth, but also about 220 petabits per second of this on-chip fabric that we're talking about, right? So a lot of wires on this chip carry data back and forth. And then you have some other extremes. You have triplets. Triplets, this is kind of the AMD approach. You design this little core chip here, which is like 8 cores. So that's kind of like, okay, considered easy to design, easy to fabricate because it's kind of relatively small chip. Then you just select the ones that work and you package them on inexpensive package. And then as the process continues, you keep scaling essentially these little chips from 16 to 7 to 5 to 3 nanometers. And you kind of eat up the yields because the chip is relatively small. And then you have this middle chip, which is the IO hub. So this one hosts all the SerDes, all the memory interfaces, DDR, etc. That one stays at 16 nanometer for several generations now, because those things are hard to design and port and validate, and they don't actually benefit from going to the next node that much, because these are analog mixed signal circuits and things like that. They don't really scale that well in more advanced digital nodes. But what you do is you kind of add some lightweight links between all of these cores and the IO, and that kind of represents a different view on the network on chip, right? It's really network on package, right? And Sophia has done some similar work in NVIDIA with chiplets and kind of trying to really kind of bring this to the next level of really partitioning, you could say like this type of design, right? Into small different chiplets that would then inexpensively talk to each other. Why? Because actually making this thing is very, very expensive, right? They still have the luxury of just shutting off some of the parts that don't work because it's a modular design. But packaging that beast is very expensive. The enclosures, the power delivery, the cooling, the stress on the wafer, all of that is very expensive. Whereas if you chipletize it and add some less expensive package, it can be a little bit more cost affordable. And then you have monsters like Ponte Vecchio. This is the GPU that Intel's planning to roll out hopefully this year. It's kind of, if you look at it, it's about a 20th of this system, but it consists of 47 different chiplets. Some memory, some compute, some cache, some IO, etc. And actually different technologies. Some are in Intel, some in TSMC, etc. So it's kind of like a mix and match platform. And they also have 3D integration. So Foveros is a way to basically stack wafers on top of one another and provide shorter routes, let's say, to memory, right? Or cache. And then an important thing for a bunch of these that are smaller is that you're starting to see board level networks. It's not enough to have one socket to do something, but because of really high demands, mostly AI applications, you need to think about how are you going to wire all this up at the board level and provide what types of connectivity and these types of memory semantic fabric networks are good for the applications you're running. So you can see rings for, let's say, ring wall reduce, which is kind of the AI way for training to kind of aggregate the gradient, or you can see all-to-all communication, things like that. So the best example of kind of that board level engineering is, of course, DGX A100 that Jensen just baked last Christmas. But you know, you can kind of see, this is a fun photo of him taking it out of the oven. That was Christmas 2020. So what you see here is basically GPU is here with 6 HBM chiplets, and then so the big kind of cooling fans or heat spreaders are for the 8 GPUs, and then you'll already see 6 switches. These are switch ASICs, NV switches, that create this basically 6 different planes over which every GPU can talk to all of the other GPUs, right? And that's to be able to have a flexible, essentially single stage crossbar, but on 6 different planes that will be able to connect all the GPUs together to be able to do this distributed computation that's required, let's say, in training, applications, things like that. So how do we understand this overall network topology spectrum, right? So there's some trade-offs going from one side to the other. We talked a little bit about the meshes, but then if you're not happy with this kind of long traversal path going to whatever your destination is, you can start trying to shorten this path. So one step is, for example, to do concentrated mesh. What does that mean? Well, I increase the rate. So in this case, the radix of my router is only 4, right? Or 5 in the worst case. So east, west, north, south, and to the core, right? That's 5. And then if I go and basically add more cores to one router, you know, then I can shrink the number of hops across the whole chip. And so in this case, I get, you know, my 4 routing destinations plus another 4 to cores. So that's 8. Then you have to look at how does the complexity of the switch or the router increase from 5 to 8 ports, right? If it's marginal, then you actually have a big win overall in the network, simply because you have significantly reduced the number of hops right now by 2x, right? So if the complexity of the router doesn't go that much up, you're actually in good shape. And then you can take that to, we'll go through some other kind of techniques. You can take that to kind of much more complex networks like CLAW that have multi-stage routing and allow you to do all sorts of things to kind of even out the impact of different traffic patterns, which is very important when you're designing something to be good for all workloads. You don't want to design something it's only good for one application. Then application changes, and this goes totally apart, right? You want to design something that for many different patterns and applications is kind of providing you uniform, consistent traffic or throughput throughout the network. And of course, the holy grail is the crossbar, as we talked about earlier, but it doesn't scale, let's say, well for our applications beyond, like, let's say, radix 16, right? So we have to be kind of careful where we use it. And so in terms of network, let's say, taxonomy or nomenclature, when someone says we're increasing the radix, right? That means we're increasing how many things we can attach once to something, right? So with crossbar, you have the highest radix because you're able, every core connects to every core through that crossbar. On the other hand, diameter means how many hops are you making through that network to reach your destination, right? In the worst case, right? And so mesh has the largest diameter, right? It's basically going all across from one end to another, whereas the crossbar has the smallest diameter. It's just one hop through the crossbar, right? And then you have a whole range in between, depending what you're doing, right? So in these types of networks, as I mentioned already, you really need a cross-cut approach to design, right? You need to know in which technology you're designing, how much power budget you have, what are your throughput targets, and then try to optimize not just the wire channels, but also the router architecture. Pick a network topology, pick the router architecture itself, the routing and flow control algorithms to be able to fit that set of applications and those power constraints. By the way, this is not kind of like a conference lecture. Feel free to ask questions in between, of course, if anything is unclear. So to tackle kind of this design problem, we want to kind of break it up a little bit. So we're going to cover kind of in this and a little bit of, I guess, Thursday lecture. We're going to be some networking basics. We need to learn kind of the basic terminology and how the basic pieces work. And then we're going to look at a little bit deeper at some of the building blocks. What are the channels between routers? How does the router organization look like? It's a piece of digital hardware like anything else. So it has its state, it has its pipelines, it has these kinds of things. And then we're going to look at some evaluations. It's very important to have this, since you're designing a cross-cut thing, it's very important to have an end-to-end evaluation framework that involves generating many different traffic patterns, simulating how the whole thing works, but then on different topologies that give you also different power scenarios, different area overheads, etc. So you're essentially seeing the cost, which is power, area, etc., at the whatever is your desired performance point, and then trying to tune the system to get it to the right place. Right? So you need this kind of cross-cut set. So we're going to first take a look at the networking basics. We already started a little bit talking about topologies, right? Mesh, C-mesh, claw. You've seen the crossbar. And then for each one of these topologies, there will be different routing mechanisms. We don't have IP tables. We don't have Dijkstra's algorithm. This is not dynamic routing. You want things to be kind of very simple, down to kind of a logic gate, deciding where you're going, right? Because the overheads associated with that cost you energy, cost you bandwidth and area. Flow control also very simple, because you need to be able to react fast, process fast these congestions, understand the buffer allocations, so to minimize the latency across the whole thing, right? And as we'll see, latency in flow control directly impacts your bandwidth as well, because if your latency is too long, you're just not going to get the buffer space. If you don't get a buffer space, your message doesn't advance through the network, and you're idling, therefore losing bandwidth. Right? So it's all kind of connected in a sense. So here's some message definitions. If you want to send a message, it will be of some size. We don't know how many, maybe a few kilobits, right? And typically, you're going to chunk that message into packets. Packet in these kinds of networks, as I said, is around a cache line size, about a typical of a kilobit. And the packet itself will have be chunked down into smaller units called flits. And these flits, will have a different type. The first flit will be kind of the header flit. That one tells you where you're going. So it's a routing information embedded in the flit. And also the sequence number, right? Because this packet has some sequence in the message. So for you to be able to assemble the message, you need to know kind of the sequence, because these packets, depending on your routing algorithm, may be arriving at different times. Right? So something at the other end needs to kind of track which packets have arrived and then reassemble the whole message, right? In case the packet is not your message, right? So there are those cases as well. And then you have basically the body flits. This is usually the payload. It's the data you're trying to send, right? Or fetch from somewhere. And then you have a tail flit, which has a little housekeeping, freeing channels, buffers, and such things to be able to kind of close off the path through which you're going. And then if you look at the flit itself, again, it has kind of a little type field, but it's where you have, is it head, body, again, or tail? Or sometimes it can be head and tail if it's a single flip, kind of just doing an acknowledgement or something like that, credit. Then you have something that we'll touch later on, which is the virtual channel. It's kind of an indicator where you're going, in a sense. And then it can also be chunked into smaller yet pieces that are typically around 8-bit size. So flits are typically around 64 bits, and then fits are essentially around 8 bits chunks. Those are kind of the smallest pieces you send across the wiring channel between two switches in a single cycle. But this is just typical numbers. Yeah.
Yeah, so I was saying that like in every message we have a lot of payload, so a lot of header and a lot of information, which is not the data. So is it like when would we want to like send the whole just the header and the rest of the data together? Because I understand a lot of bandwidth is being allocated in just transferring this head data.
Yeah, that's a good question. So the question was, let me paraphrase it a little bit. It's the balance of the header information versus the payload, right? The data. And it depends on what type of network what is it exactly for? We'll see later when I show you a Tylera example, they had like 5 different networks on chip on top of one another, each serving slightly different application and having these different trade-offs. But in this case, it's not actually that much if you look at it. If let's say a packet was a cache line, right? So 1 kilobit, the header would be like 64 bits. That's why you chunk it into flits. Flit could be even smaller, 32 bits. And you try to minimize this stuff, routing information. I don't want to have like a 16-bit or 32-bit string telling where I'm going. I want to have some simpler tag, as we'll see, or use dimension order routing to really simplify that overhead, right? But you're right, it is definitely always a balance of what's the header kind of information, the bookkeeping in the network versus all the payload that you're sending. Yeah. So basically, that's this whole thing here, is that if you think about it, for a given size network, I have to have this routing information, even if I have a very clever way of shrinking its size, it's going to be some size. So if I go too small on the packet size, then the proportion of that fixed header to my payload is going to be high, right? And I don't want that necessarily, because you'll see later why also shorter packets or flits are more beneficial. So I'll have some benefits, but I'll also lose on my throughput, right? Because I'm just going to be sending many more headers compared to the bodies that I want to send. So there's kind of a trade-off between, let's say, latency and throughput in this system, right? So that's exactly this kind of piece that I want to show you. You have several different, yeah.
Another question.
Uh-huh.
It says send across channel in a clock cycle.
Yep.
Isn't everything sent across channel in a clock cycle? Why only that part?
So fit, I mean, it's just, think of this as kind of like a notional structure, right? As an architect, you can decide, for example, that fits are not needed, and the fit and flit are one and the same thing, depending on, let's say, how many wires you have physically connecting one router to another, right? We call that a channel, right? So if you have, let's say, 32 wires, right? It doesn't make sense to send only 8 bits on these 32 wires. You have 32 wires. You might as well declare either a fit to be 32 bits, or say, oh, my flit is going to be 32 bits, and I'm done, right? But this is in case, what if you have only 8 wires? Right? There's a lot of cores, significant routing congestion for all the other stuff. You may have different types of networks, like I'll show you for Tylera. So you only allocate 8 bits. It's a narrow channel. Then you have, your flit is 64 bits, because let's say that's very convenient for other message sizes and things like that. Well, now you have a way of serializing that 64-bit flit across this smaller channel. So you need to kind of chunk it into some smaller logical unit, right? And that's what the fit is about. Yeah. So the zero load, the latency. The first thing we're going to look at is zero load latency. This is something architect can estimate with pen and paper. You don't need any simulator to be able to figure out what this number is, but it's very useful back on the envelope number to tell you the performance of your system. And so we label it T0 because zero low latency means there's no congestion, there's no flow control induced basically penalty on the latency or the throughput, right? So here's kind of what all the components are. So you're gonna do TR is gonna be our router delay, right? From when you enter the router or switch to when you exit, there's some mechanisms there. There's some number of clock cycles you have to pay depending on the type of router. So TR is that. Hmin is the kind of average minimum number of hops. Like if you looked at some network for uniform random traffic, what will be the average size of the number of hops you need? Because you will be changing destinations from the furthest out to the shortest with some uniform distribution. So you can say the average is going to be maybe 8 hops, right? So Hmin will be 8 router delays. Then you have Dmin over V. That's basically, okay, for that average distance that you calculated, you have to travel under some traffic distribution, right? There's certain signal velocity at which you're going to be propagating. If you're using equalized interconnects, like we'll see later, you get a little bit faster. If you used repeaters, or you use repeaters with flops, you know, registered kind of repeaters, that's even more latency to get through that channel. So that this gives you kind of the channel delay, just getting across the wires, whichever way you picked is your kind of implementation way. And then the last component here is what we call serialization delay. And this serialization delay is basically the length of that unit that you're sending, L, over the bandwidth. And bandwidth we're just expressed here as basically, let's say, bits per cycle or bits per second, whatever you want, right? So here is kind of where that, why this partitioning to smaller things matters, right? If your message is long, let's say you decided to stay at 64-bit flit size, right? And on the other end, there's nothing you can do on a smaller unit than 64 bits because you need that information within the flit to advance. Then you gotta wait for 64 bits, let's say divided by 8, which is our example channel width, right? You have to wait for 8 cycles for the whole thing to go through so you can use it. But if fit was something you can use immediately to continue routing, then you only send 8 bits and everything else is kind of pipelined behind it, but you keep going. So you don't pay that serialization delay right there, right? You will eventually have to pay that serialization delay somewhere, depending what size of the message you're using, right? So somewhere you're gonna have to assemble the whole message, and only when you assemble it, you're gonna be able to use it. And that's where you pay this whole serialization delay, right? That's why it's kind of nice to have very big channel bandwidth, right? Very big router bandwidth. So you can just instantly soup all that, but that unfortunately costs you power and costs you area, a lot of wires, a lot of repeaters, a lot of flops. So that's unpleasant, right? Okay, ideal network throughput and capacity, what we call capacity. Oh, yeah.
Sorry, in the previous slide, is there a reason behind why we choose this? Because in this case, what would be approximating the lower bound?
This is, let's call it average minimum, right? What this means is that you have a choice where, let's say, how many hops you could make, right? I could, given, let's say, a mesh topology, I could be making always the longest. If I pick my destination, there are multiple paths through that destination, and I want the shortest path. So if I do, how I'm doing the average is I'm generating a uniform random pattern and saying, okay, every core has the same likelihood of being accessed. What is the minimum path to that core, right? And then I'm going to average all these minimum paths. If I'm going to my neighbor, I'm not going to be going all the way around and then back and averaging across that, because that's a bogus path. Now, we will see that for some traffic patterns and congestion things, you actually want to do this, especially in meshes, because they can get bottlenecked. You actually want to do this randomized middle node routing. And that way it becomes a little bit different how you calculate this average minimum, right? But this is kind of like an extra second order type optimization. Vanilla is you basically just look at the minimum path and average across the whole uniform pattern.
Because algorithmically speaking, you usually pick this one, the shortest path.
Yes and no. As I said, in networks, it depends kind of what matters to you. Does the fairness matter? Does the overall throughput matter to you? On which types of patterns? There are some patterns that, especially for meshes, are kind of very nasty in that they create specific bottlenecks in certain parts if you have deterministic routing. We're going to touch on that very soon. But then you can randomize the routing so that these kind of bottlenecks don't happen, right? The overhead of that is now introducing some longer paths to get to the destination. But the good news is you eventually get there. Whereas if there is an anomalous traffic pattern, you may always be hitting like a buffer overflow and never get there, right? So those are kind of the slight differences there. Okay, so how do we compute the ideal network throughput? We looked at ideal latency, right? Which is zero load, what best I can do. And now what's the ideal throughput? Well, this is kind of the maximum traffic at which the cores can inject stuff into the network, right? And still get the work done. Meaning there's no overflow dropping of packets. You're actually injecting and stuff is going through. So if you look at kind of the mesh throughput, this is an example here. An important quantity or thing to think about is what's the bisection bandwidth of the network, okay? And we've drawn it here, right? So bisection bandwidth is basically something that defines the bandwidth that we're across a cut that has half the nodes on one side and half the nodes on the other side, right? So in this case, it kind of looks easy. I just cut it here in half. Half the cores are on one side, half the cores are on the other side, right? And then I calculate the bisection bandwidth. Well, I have B, which is the bandwidth of each of the channels. So each direction of the blue arrow is basically B, right? I have two directions across the cut. One direction is this way, another one is that way, so it's 2B. And then I have square root of n of these bidirectional channels, where n is the total number of cores. This is just by like square organization of the whole thing, right? Now, you contrast that bisection bandwidth with the data that was generated by cores and needs to cross the bisection cut, right? So what does that mean? Well, every core injects into the system at some rate, and we call that B core, right? And I have n cores. And so if I look at these n cores, this is n over 2, right? If they generate uniform bandwidth, half of what they generate stays here, half goes across. Because it's uniform, 50-50 probability that it's going to be on this side versus that side. Same thing is for these cores. Half of their stuff stays, half of the stuff goes across. Right? So that's why we get this 1/2 of the overall generated bandwidth actually makes it across, right? And then you just equate these two, right? So you say, okay, what is then my ideal throughput? That's n times b core. How much can all the cores inject into the network, right? And that ends up being 4 times square root nb, right? Now I can size my channels, right? If I have a desired throughput, injection throughput, b core, I have the number of cores. For this topology, I can select b, which is the width of the wires that I have between the two routers, right? And see, does that make sense? If it doesn't make sense, probably need to go change the topology, right? Okay, that makes sense. I think this bisection bandwidth concept is very important. And for different network topologies, you'll be able to quickly do a bisection, calculate what the throughput is, look at kind of the uniform traffic pattern, let's say, quickly understand how much traffic is going across that is being generated by nodes, and try to balance the two and see, is the system balanced? Maybe the architect screwed up and they just like completely missed and over provisioned the channels or under provisioned the channels compared to what they're trying to inject. That can also give you an indication, are they really sizing things for uniform traffic or maybe for some other localized application and the network is just kind of there to do something less kind of heavy. Okay, so these network performance plots is something that's very, very important. In the end of the day, that gives you the full picture. What we have kind of looked so far at was this theta ideal, right? That's just back on the envelope calculation. And then we looked at this basically H mean TR, if you include the effects of routing, H average TR, and then if you include a little bit of the effects of the flow control, then the full T0, which is zero load latency. The issue is that every time you include this next layer, how the routing is done, how the flow control is done, your throughput also drops. So, and these are things that are harder to kind of do by hand. You really kind of need to get into the network simulator for a given topology and understand how much this shrinks. You'll see later in some plots that I show you, this can shrink by 2 to 4x, depending on the real simulation and the types of traffic patterns you're running on the system. So, you know, FFT, for example, has totally different pattern, although it's global, than like uniform random. And then some patterns like tornado, or there's some like very malicious patterns you can construct for every network type that completely block the network, right? So these are kind of important things. One type that's kind of like a twist on the mesh is Tori or Torus, right? So what you do, it's basically a low radix, simply because like mesh, routers have very few ports and large diameter. It needs a lot of hops to get to destination. But what they do is they provide these like return pods to kind of complete the circle. So if you think about it, it's kind of like a ring, a bunch of rings that are connected together. Or in terms of mesh, you're just completing a hop from first to last, right? The nomenclature is NRE K cube, which means NRE stands for number of nodes per dimension. Like in this case, it's 4 in X, 4 in Y, so 4 RE. And 2 cube is basically for the number of dimensions. We're like sitting in 2 dimensions here. There are also 3D Tora, etc. So many different types of networks. If you're talking about kind of the rack scale architecture, so you need to do both plane and across, and so you can scale this up. And then you see kind of the nomenclature for the mesh. This is 4RE2 mesh, 2-dimensional mesh, 4 nodes per dimension, right? Now notice that if we kept the channel the same for both of these, as I make a cut, right, I have twice more channels because of this return path, right? So my bisection bandwidth grows by 2x. And so I can then plan for that in basically my design, right? Okay, I mentioned tile 64 a few times. This was one of the early examples of this, like, let's say, relatively large 64 cores ASIC. And the interesting thing here, just historically, is that yes, it was a simple network, 5-port routers, full mesh. It was actually 5 different meshes on top of one another, each dealing with a different architectural requirement or application requirement, right? So just to give you an example, I mean, this is kind of how the whole thing looked like. So you had a processor, a switch, and a local cache that goes all the way to L2. And so this is kind of now your unit that you just stamp across the whole chip. So pretty easy kind of design. Of course, you have to have all these other infrastructure just to connect the chip to this memory network that we talked about, right? That you also need. But as you see here, they have like 5 different types of networks. Static network allows you, it's kind of like a VLIW or pre-compilation, right? You have a data flow graph. You can pre-compile for the, like for AI training, right? You can pre-compile the whole traffic pattern from start to end of the application, right? To do that, you can essentially orchestrate this network to switch at the right times as the application is running, so that to minimize all these overheads with routing the packet, buffer, contentions, because everything is predetermined and optimized at once. And then you of course have dynamic networks for essentially workloads that are not statically, or you can't pre-code them, or you cannot statically compile them. So you have branch predictions and all sorts of things that you need to deal with. And that's where these dynamic networks are in place. And then you have also this UDN, IDN. It's kind of an interesting network that just bypasses the whole cache thing and just connects all the ALUs together. So you can string, kind of in a systolic fashion, string the arithmetic operations across the whole chip, right? And this is more like a research thing. They're just trying to understand which blends of these networks yield you best performance for what type of applications that you're running, right? It's not that you really need all these networks on chip. It's just you want to try to figure out what's the best sweetest spot to have. Now, in improving these tori that we talked a little bit about, is you can think about kind of the trade-offs in wire complexity. And again, adding a little bit of ports to your routers. One way is not just through concentration, but also by adding these express pots, right? So what we're doing here is we're saying, well, this is how unfurled your whole like tori kind of, let's say 16-array express cube, right? Looks like. But you can decide to basically every 4 channels add a bypass, or every 4 routers. So you essentially don't have to wait to string along the whole dimension of the network to the edge of the chip. You can kind of bypass. If you're going to number 4, boom, you immediately go to number 4, right? You don't wait 16 in line over there. And so you can do that. You can add extra channels, make this spot faster than these spots, because you're saying, okay, this is for like hyper traffic. It's kind of an analogy of freeways and streets, right? Freeways don't have that many exits, but they get you there faster, right? Butterflies also try to minimize the number of routers connecting the nodes. So some nomenclature here is NREK fly, so n nodes per switch. In this case, it's 2 nodes per switch. So it's 2 RE, and 4 fly is how many switches are in the pot. Right? So this will be one example where you connect 16 cores to each other. Notice that these numbers here are the same on both sides. So these channels are basically unidirectional, not like in the mesh, we talk bidirectional. So when you're calculating bisection bandwidth, be careful about that. You know, there may be a homework problem on this. So just make sure that you understand which nodes talk to which nodes in the network, right? The way typically people build this, because obviously node 0 here and node 0 here is the same thing, right? That's processor 0. So the way this is kind of a logical representation. Physical representation is that this is folded, right? And so you got to think a little bit about that when you're thinking about floor planning your chip and mapping different types of networks. Same network topology, logical, can have many different floor plans on the chip, and each floor plan has impact on power, bandwidth, area, etc. Right? I'll show you some examples of that too. Butterflies do shrink the number of hops compared to meshes, right? But just like meshes, they have this problem of no path diversity, right? So let's say in this case, I want to go to this group of 4. There is basically a point, a branch here, where let's say this group of 2 and this group of 2 will collide if they want to go to groups to processor 0 to 3, right? And there's nothing you can do about it. And if the traffic application is such that that's exactly what's happening, you're going to have essentially a problem. So to be able to, that's why they call it inherently blocking, because this group can block this group from ever reaching here, or at least half the time, as long as they constantly send stuff, right? And so shuffle permutation, that's like, as I said, you can always identify kind of bad patterns that can basically tear down a certain network topology. And so this is shuffle permutation is kind of bad for this one. This has been fixed in the claw network topology that we're going to take a look next. This is, you know, what is it, 69 years old network topology, grandpa, but still pretty good, in pretty good shape. So here we have 8 array 2 fly butterfly, right? In this nomenclature, we have 8 nodes per switch. We only have 2 switches. The problem with that, it's kind of actually pretty nice. It's only 2 switches, right? You get across pretty quickly. But let's say this is a path that is basically not redundant, right? So all of these 8 nodes have to kind of compete for this one path. That kind of causes a lot of congestion among these 8 nodes if they want to go to this group. There's no other way. That's the only one channel you have to use. Okay? What Claw does, it adds a 3rd stage of switches. And now from this group of 8, if you want to go to the same group of 8, you can choose the middle switch to go through. It's either going to be A or D, right? Or any other in the group, right? Because you're going from this first switch to all of these, and all of these go to the 3rd stage. So you have plenty of choices which path you want to pick, right? Now, freedom is good, but with freedom comes the responsibility to choose what you're actually going to do, right? So that's a little bit of an overhead that you need to pay in Claw to kind of figure out where from here, even if you're going to this same group, you need to kind of know through which of these switches you're going to go, right? You need to make that request. So the routing algorithm has to make that decision. Is it going to be deterministic, always first switch? Well, that's going to cause congestion because everyone goes through that switch, or it's going to be something more randomized. And we're going to touch on that when we get to the routing. Here is an example of what I was talking about in the differences of logical to physical mapping, right? So we're talking still about this Claw network, right? So you have 3 stages of 8 routers, each are labeled 1 through 8, A to H capital, and the last A to H lowercase, right? And so you have some choices. How do you want to put these routers on the chip, right? You could say, I want a highly regular thing. I want to design basically a group of 8 processors, put my router, basically all 3 router switches in the middle, and then just let it place and route in between according to the topology. Potentially a bad idea, because you may be having wires that go all across, simply because you need to kind of reach, depending on kind of how you're routing. Remember, you need to go from each one of these to all of the others, right? So if you put these A, B, C, D, E, F, G, if you put them, each one of them in each one of these little things, right? That means that my first stage router needs to make it to here, then to here, then to here, then to here, right? And then of course across to all of them, right? So my longest wire is essentially almost the size of the two edges of the chip. Right? That's pretty bad, because it's going to limit all the other wires. I can't have one switch to switch traversal last 2 cycles and another one last 1 cycle. Everything has to be kind of uniform. So that's bad. Now, if you put everything in the center, all the middle switches in the center, then you kind of cut basically almost by more than 2x the longest wire route. Right? So you can save some power, save on the latency as well. Okay. It's very useful, as I said at the very beginning, to use the zero load latency calculations as well as the bisection bandwidth, ideal throughput, to be able to do quick topology comparisons as you're like evaluating stuff for your application. So this is kind of like a summary. We're not going to go through every line, but I encourage you to go and take a look. For example, the goal here was for these 4 topologies to say, okay, I want to size them, size the channels such that I can inject the same bandwidth from each core, let's say 128 bits per cycle, to saturate. So I want the same throughput of my system. And of course, under uniform traffic, it's going to saturate kind of the bisection bandwidth. So I will be able to choose, because these are different topologies, different number of wires in the bisection channel, depending on topology. And that kind of makes things work out here. And then, of course, my latencies will be essentially larger. And then basically you see here that mesh has the widest spread of the latencies, depending on where you're really going. In the worst case, you're 46. Fastest case, 7. Pretty good. Whereas crossbar, it's actually 1 hop, but there are, depending on this is a 64 radius crossbar, so it needs a lot of stages to just get across that size crossbar, and it's logic, right? And then claw has kind of a narrower distribution and things like that. Okay. Oh boy. Okay, routing algorithms. We already touched a little bit on this, right? Simplest case is everything is deterministic. Simplest hardware, most predictable. The problem is it basically poor load balancing, like in the claw example, this would ignore the path diversity that's available in the network topology. But the nice thing is that, you know, it's quite common in practice, and they're basically easy to implement because of kind of the deterministic nature, and also that you can make them deadlock free, meaning that the deterministic route will basically make sure you don't have kind of the feedback deadlocks that are sometimes possible if your algorithm is less deterministic, right? So you can't really verify if you're going to run into this condition. Oblivious algorithms are basically ones where you just let fate decide. So the easiest, simplest kind of implementation-wise way of dealing with some decision you need to make is to toss a coin. And that introduces kind of a random distribution. So in the claw example, the middle node that we're going to pick would be a random toss. Right? So it's kind of predictable, you know, what your algorithm is, but the middle node will be kind of uniformly distributed, and hope is the load will be kind of uniformly distributed across those. And then adaptive algorithms are kind of the best in a sense of the intention, right? I want to know what's really running, how the queues are occupied, and really kind of optimize for that. But all that requires a lot of hardware overhead and can lead to, because of the latencies in communicating this state across the system, it can actually lead to imbalance. Right? Just like any control system, if you had too much latency, phase margin goes down, it will be basically, it starts being more likely unstable. Right? So you need to be really careful to not overdo it and still have very short feedback latency spot for the state updates to be able to make meaningful decisions. Because basically, at some point, you're just going to be too late. You're observing something, but that condition has passed. Now you're applying that correction to the wrong place, and the whole thing goes nuts. So an example of deterministic routing, on the right-hand side, we have what's called dimension order. So for Tori or meshes as a subclass, where you have strict network dimensions, like in 2D mesh, it's X and Y. In 3D, it will be X, Y, Z, etc. Right? All your routing needs to do is say, okay, go X 3 times, go Y 5 times. That's it. Right? Very simple. It's always going to be like that. On the destination tag, this is more for like butterflies and claw type networks. Each node has basically a tag, and in each router you peel off the direction. Every channel is labeled 0, 1, etc. And you just peel off the binary direction, and you're essentially there. So you don't have to really infer where it's going. You just peel off parts of the destination tag, and you make your routing decisions that way. For the oblivious routing, as I mentioned, I already kind of mentioned this claw example. Once you're in this switch 1, you need to decide where you're going, which middle switch you're picking, because any of them can take you to the group you want, right? So you flip a coin, 8-sized coin, and you get a number, and you go essentially to that one. That way, you're kind of randomizing the traffic across all of these switches, so you're trying to avoid this congestion. It's a little price to pay to be able to leverage that degree of freedom that you have in the system compared to butterfly, right? A folded claw, it's kind of just it's also called a fat tree. It's kind of more implementation friendly topology, because as I mentioned already, you're just taking this side and folding it back here, since basically they're all accessing the same thing, right? Same nodes. So here, you actually don't have to go as deep. You can come back earlier. So if I'm going from this group, I only need to make it to this stage, and then I already have the ancestor path back. I don't have to go all the way to the 4th stage unless I'm accessing this other group over here. And so here, let's say you can pick the nearest common ancestor switch. That's like a heuristic, right? To be able to do it. Yeah, flow control. Flow control is this line. So we went through basically the routing piece already. The network topology was first, routing, and then basically flow control. There are 2 types of networks. Even though we talked just about messages and packets, the kind of simpler type of network is circuit switching, which is kind of the oldest network we've had. Basically, that's in the phone lines. You pick up a phone in the old times, not now. Now it's packet switched phone network, but like the wired phone network is basically circuit switched. You pick up a phone, someone reserves your whole circuit, you talk as much as you want. You put down the phone, the line breaks. Someone else can use that some part of that connection, right? So that's bufferless flow control. Once you have reserved the path, it's yours, and you know that you don't have to kind of buffer along the way because there's no collisions. You own the path, you just keep sending as fast as you can. Right? As we'll see, that comes with overheads, because reserving that path, especially if it's a long path, takes actually a long time. So once you reserve it, you better have a ton of stuff to send to amortize all that time you waited to get access, right? So it means if it takes you 15 minutes to set up a call, you better talk for 5 hours rather than 5 minutes, right? Because you've lost a lot of time. Now in buffered flow control, once you introduce these buffers in the path, you can actually packetize whatever you're trying to send across and send it in smaller pieces and send it through possibly different routes and then reassemble all that at the other end. But then it lets others use the same medium concurrently, kind of in a time interleaved fashion. And so there's a lot more different algorithms there. I'll touch kind of briefly on each one of them. You can, again, make these routing decisions or flow control decisions based on the whole packet, or say, well, gee, that's taking a lot of resources because my packet is big, let's say it's a kilobit. I'm going to make all my decisions based on a smaller unit, which is a flit, and then let others kind of reuse these same resources on a flit scale. So it's kind of the granularity at which you decide to share, right? And that gives you some different routing algorithms, but also different efficiency curves. Right? And then there is a way, how do you manage the buffer overflows? Because inevitably, if many people want to talk to the same buffer, you're going to get an overflow. So you need credit-based, for example, or on-off or flit reservation. Credit-based is like, for each sender, they have a stack of credits, which means the downstream buffer has allocated to them some space. If they keep sending, they fill that space. The downstream buffer, basically for everything they send, they decrement their credit. When the downstream buffer empties, it gives them 1 credit back, so they up the stack. And so everyone knows essentially how much they can send. The problem is that knowing costs you round trip latency of getting that information, and that actually basically sets your throughput and also sets the buffering limitation. So we have some calculations to show for that. So this is the circuit switching, right? As I mentioned, and R is a request. So what we're doing in this example, let's say you have 5 channels to traverse, right? 0 through 4. You got to make it through every channel and request for that channel to be yours, right? So you make it through 3 channels, and let's say the 4th channel is blocked. You got to wait for that channel to clear up, someone else to kind of finish their phone call. Then you make a request to reserve that channel, part of the channel, and you make it then all the way through. The good news about circuit switching is that even though we had to wait here, the request is not lost. So the request is kind of like controlled and buffered for the time the request can make it through. Once the request makes it through and creates a circuit, then data zooms through, right? So here we had to pay a little bit of time for waiting to get the request through, but we didn't kind of have to retry all the way. That's what I'm saying. It didn't get dropped here. Packets will eventually get, or flits will eventually get dropped. And so you have to kind of resend in that situation. So we made it all the way through. Now we basically acknowledge that the channel is there, that the sender can start sending, and then the sender starts sending loads of data, right? So this is the first packet or chunk. This is the second chunk with some spacing, depending what the application is. And then this travels in a kind of pipeline fashion through all these channels, right? And in the end, you have a teardown. Teardown basically just releases all the channels that have been reserved, right? Very simple to implement, but notice how much time we spent in setting up the channel compared to communicating, right? So unless we had many of these data chunks to send, it's not really worth it. It's like 50% of the channel utilization just went on setting up the circuits, right? So people actually experimented with these ideas. So Anderson from Intel Labs had this I believe it was 64 core 2D mesh that was like packet circuit reconfigurable. So you can play with different traffic scenarios and understand kind of the trade-offs there. So some interesting things, of course, that you can see logically is that as the number of hops increases, right, your effective throughput goes down because of this overhead of time that it's required to go and set up the channel, right? And certain things like that. And then they're playing with kind of the trade-off of packet cycles to circuit cycles. Again, you see that as your circuit clock cycle, meaning like how long are you using, how long is your message, right? If that reduces, your throughput also reduces because the overhead proportional to payload you're sending is smaller, right? So things like that. And then you have this other extreme, which is packet buffered flow control, right? So the thing to notice here is that both buffer and the channel, so buffer is of course part of the router, and the channel in this scheme are allocated to the whole packet. So it's not just flits. You have to receive the whole thing. So store and forward, you have to receive the whole packet. Then you decide where you to which port you're going, and you have to make sure the next router has also enough space to accept your packet, and that output channel is free. Then you can advance, right? So this basically, if you look at the latency calculation, this wraps this serialization delay straight up with the router delay, and then you have to multiply with every single hop you make, because you're not routing as soon as you get even a little piece. You're waiting for the whole thing to come in, then making a reservation request, doing it again and again, right? So you're paying the router plus this, and of course there will be another component here, which is just the channel delay itself, right? That repeats that much time. Now, cut through tries to avoid that accumulation of serialization latency. So it goes and says, okay, well, the only info I need to know where I'm going is really in the head flit, right? So soon I get the head flit, I can start going and making reservation requests. In cut through, the trouble is that, so that sounds good, but the trouble is the reservation request made is still for the whole packet because they don't want to kind of lose any piece of it, right? And so that is not an effective usage of buffer storage, because let's say that the downstream buffer has only 4 slots available, right? But my head flit is making a request for 5. Well, it's not going to be granted, right? And my head flit is not going to advance. In fact, nothing is going to advance. We'll see later in the flit-based algorithm, if there's 1 slot, my head flit can advance, the rest will stay, right? And that still makes some progress through the network, because in the next cycle, maybe another slot opens up, so my body flit can go, right? So it's kind of this granularity of decisions, but at least cut through basically gets rid of the serialization problem, right? So it solves the serialization problem, but doesn't solve the kind of resource utilization problem, right? And resource utilization can affect your throughput, right? As well as kind of the effective latency in the system. So that's why people kind of shifted to flit-based buffer control. And so wormhole is basically one algorithm that leverages that. And so let's say in this example, right, we have the head, body, tail flits that we're trying to send. So head flit makes it into the input buffer here. Input buffer has 2 slots, so body flit can also make it in. And now the state is figured out where you're going. So the internal channel in the switch is allocated. So I can now traverse the switch and get the head flit out, right? And then I can get the body flit out of it, tail frees up the storage. But in this case here, we had that the channel is blocked, let's say for some reason, right? Because both of these are full. So I can't advance the third one. Only when the switch is allocated, I can advance the head flit and then accept another body flit. But I'm still kind of making progress, right? I pushed out at the input, I had these two, then I had nothing. And then, but at the output, I got them all basically assembled without the delay. Okay. Now, this is kind of effective because I'm dealing now with flits and I'm reserving the buffer. I'm being able to make headway just based on what downstream stuff is available for a single flit, not for the whole packet. But I still can get kind of, let's call it head of the line blocking type of thing. It's like the thing you're trying to turn on the right on the red light, but there's a guy right in front of you who wants to go straight, right? So you should be able to go if there were not them, right? But they're going in a different direction. So there should be some way to deal with that, right? It's multiple lanes. It's just that if they park in the wrong lane, then you have a problem. So here you have another twist on this, which is called virtual channels, which solves the wormhole problem. And this one basically wormhole, if this downstream channel gets blocked, you're not going to be able to advance stuff from this buffer out because the downstream channel is blocked. So that's going to backdrop essentially this make this channel idle, right? Now, if you have virtual channels, so you can do allocations based on from the same input port based on where they're going. So pick which one you want, right? Then you actually can route, for example, in this case here, you know that this one is blocked, but this one is free to go to this other channel. So it will free up this buffer so that this whole path can advance and you can leverage this channel over here. So it's kind of making this channel idle and now it's utilized because some other flow can actually do it. Okay, I think we're good on time, right? A bit over. Okay, sorry for keeping you a few minutes, and then we'll finish some of this stuff on the Thursday lecture. Okay.